In this video, we're going to talk about the pH scale and what it means in relation to acids and bases. Recall that acids are substances that donate or give off H plus ions in solution. Bases are substances that accept or receive H plus solutions. If bases act in the presence of water, that means they're in aqueous solution. And if you think about what that means, the bases are going to receive H plus from water. And when water gives up the H plus, it becomes OH minus, hydroxide. So in effect, bases, by accepting H plus from water, produce OH minus. So really, when we think about pH, we're talking about the balance between hydrogen ion and hydroxide ion. In a neutral solution, those concentrations are equal to each other. In acidic solution, hydrogen concentration is greater than that for hydroxide. And in basic solution, it's the opposite. Hydrogen ions are less than the hydroxide ion concentration. The pH scale can range. Theoretically, there's no limit to the smallest value or the highest value, but almost never would you see values outside of 0 through 14. Let's take a look at this chart. At the top, we see pH numbers 0 through 14. In the next line down, we see hydrogen ion concentration. And notice how every time there's a step of 1 on the pH scale, the concentration of hydrogen ion goes down by 1. So from 1 to 10 to the negative first, that's a divide by 10 change. From 10 to the negative first to 10 to the negative second, divide by 10 again. 10 to the negative second to third, divide by 10. At the same time, hydroxide ion concentration is going up by 10 with each step on the pH scale. 10 to the negative 14th, if you times that by 10, you get 10 to the negative 13th. And times that by 10, you get 10 to the negative 12th, and so on. So every difference of 1 on the pH scale corresponds to a 10-fold, which is a fancy way of saying 10 times difference in hydrogen concentration. It's really important. In the neutral solutions, let's take pure water right in the middle, pH of 7. Notice that the hydrogen ion concentration is equal to the hydroxide ion concentration. Take an acidic solution, something with a pH less than 7, like coffee. The hydrogen ion concentration 10 to the negative 5th, that's a bigger number than the hydroxide ion, 10 to the negative 9th. Take a base like detergent with a pH of 11. The hydrogen ion concentration 10 to the negative 11th is a much smaller number than the hydroxide ion concentration of 10 to the negative 3rd. So the concentrations are equal in neutral solution. Hydrogen's bigger in acidic solution. Hydroxide's bigger in basic solution. The whole pH scale is based on water, and it's a logarithmic scale. So meaning a difference of 1 is a 10 times difference. And that means that when we go to calculate with pH, we're going to be using the log button. You might know that from math class. Okay, here are some things about water that really set up and define the pH scale. For one thing, water is amphoteric. Water can act either as an acid or a base. When it loses a proton to become hydroxide ion, it's acting as an acid. When it gains a proton to become hydronium ion, it's acting as a base. Water reacts with itself. We say that it autoionizes. That means it breaks apart. One water molecule reacts with another, pulling a hydrogen away from it. And when it does, it forms equal numbers of hydrogen and hydroxide ions. That's really important. So that means if we've got equal concentrations of hydrogen and hydroxide, well, in any collection of water molecules, no matter what the size is, the concentration of hydrogen times hydroxide is a constant. It's 1 times 10 to the negative 14th. This is going to be a really interesting equation, and this equation will provide one of the formulas that we'll find helpful when tackling problems in just a moment. Lastly, Since any solution that we consider in class is going to be mostly water, we're only going to deal with aqueous solutions. We can assume that it will behave like water, and thus the whole pH scale is going to be based on this water-like behavior. Okay, let's give you some formulas. These formulas will be provided on tests and quizzes, so you do not need to memorize them, but you do need to know how to use them. First, pH equals the negative log. You might remember from math class that there's two kinds of logs. There's natural log and base 10 log. This is the base 10 log. It's spelled log. The other one is ln. So if you take the negative log log of hydrogen ion concentration, we'll get pH. It turns out this P function is really a mathematical thing. If you take the negative log base 10 of anything, you're finding the P of that thing. Let's say that you know the pH, but you don't know the hydrogen concentration. Take the number 10 and raise it to the power of the negative pH. 10 raised to the negative pH will give you the hydrogen concentration. And since P is just a mathematical function, you can also use it to find the pOH. This is kind of like the forgotten cousin of pH. Negative log base 10 of hydroxide will give you pOH. And likewise, if you knew the pOH but didn't know the hydroxide concentration, you could find it by taking 10 raised to the negative pOH power. These are all ways of quantifying how many hydrogen ions and hydroxide ions are present. It's just a convenient way of representing that. Now, back to that one equation. If the concentration of hydrogen times the concentration of hydroxide in a water sample is always the same number, 10 to the negative 14th, if we take the negative log of each term in that equation, we arrive at this. The negative log of hydrogen is pH. The negative log of hydroxide is pOH. And if you times something, when you're taking log of it, you add it together. And the negative log of 10 to the negative 14 is 14. So we have this wonderful equation that links together pH and pOH. In any aqueous solution, pH plus pOH equals 14. We're going to use these formulas in the next sample problem. Please grab a calculator if you have one. Let's get going here. Question 1, what is the pH of a solution that contains 0.078 molar HCl? First of all, I want to point out one little side note. HCl is a particular kind of acid. It's a strong acid. And so I can get away with asking about the pH of a solution that just has a certain concentration of the acid itself without specifying the hydrogen ion because it's a strong acid. Turns out this is a pretty straightforward calculation. If pH is negative log of hydrogen concentration, we're simply going to take the negative button on our calculator, and please note that that's different from the minus button. So look for the button that has a little dash in parentheses. On a TI calculator, it's typically below the 3. And then look for the LOG button, usually along the left edge of your calculator. So negative LOG, and then your calculator will open up a set of parentheses for you. Type in 0.078 and hit enter. You should get some number relatively close to 1.1. Here's that side note I mentioned. The assumption that hydrogen ion concentration equals acid concentration works only for strong acids. In our next lesson, we'll talk about the difference between strong and weak acids. Question 2, what's the pOH of this solution? Well, if we know that one of our formulas was the pH plus the pOH equals 14, and we know that the pH is 1.1, all we need to do is subtract 14 minus 1.1. And when you do that, you get 12.9. That's a pretty straightforward calculation. You might not even need a calculator for that one. Question 3. You'll definitely need a calculator for this one. What's the OH minus concentration for this solution? We know the POH, but we don't know the hydroxide ion concentration. So to undo the log, take the number 10 and raise it to the negative POH power. So on your calculator, type in 10, look for the upwards caret button, and then type in the negative button, 12.9, and hit enter. I'm going to round to 3 significant figures, so 1.26. And then I want you to look all the way to the right edge of your calculator. It might say E negative 13, or maybe it says times 10 and then raised to the negative 13 power. It's important to write that down because there's a really big difference between 1.26 and 1.26 10 to the negative 13th. Big difference in numbers. So yes, I need you to write down every exponent that you see on your calculator, but no, I do not need you to write down every single decimal place that your calculator gives you. I want you to round those numbers, but I do want you to include the exponent if there is one. The last thing I'd point out is, since they're asking for a concentration, we're going to give a unit, molar, write in M for moles per liter. All right, good luck on the homework.